Okay, I want to take a few minutes to introduce rotational motion, which I cover in Unit 7, which coincidentally enough is when the unit from the College Board on the suggested unit in AP Physics 1. In reality, we spent Units 1 through 6 on linear motion. We could have easily spent the same number of units talking about rotational motion. In other words, everything that we're going to talk about rotational motion could be spread over 6 units. We're going to cover it in one. And here's what I tell my kids. The better they know linear motion, the better they're going to understand rotational motion. Because the word for the unit is analogous. And that's what I keep repeating that. That's the word. Rotational motion is analogous to linear motion. Different terms, similar meanings. Different equations because they have different terms, but they basically are the same equations. So let's define rotational motion. And I tend to get real lazy and I write it as ROTMO. I don't think that means anything bad. I don't really know. Basically, the object is spinning about an axis, about an internal axis. Now, the Earth is revolving around the Sun, so the axis of rotation is in the Sun. The Earth is spinning. That's the rotational motion about an axis through the Earth. So that's what I mean by about an internal axis. It's spinning about an internal axis. Now it's actually a little bit more than that, but that's okay, and that's a pretty fair enough good definition for what we're going to be dealing with. So before I jump into all the big ideas for the entire unit, let me kind of introduce rotational motion through the vocabulary, because that's what really makes it different than linear motion. I'm a big proponent of vocabulary. I firmly believe that the better the kids are able to understand and use the vocabulary, the better they understand everything that we do. I often give the analogy of it's a foreign language class. And when you go into a foreign language class, when you go into a Spanish or a French class, you're expected to speak in Spanish or in French or in German, whatever the language is. When you come into my classroom, I expect you to speak in physics, using the proper terms of physics, understanding the proper terms. Otherwise, you're speaking gibberish. And that's a lot with the AP Physics 1 test. They want to hear you have to be able to communicate. So I'm going to put up not all, but a bunch of the linear terms, and then we're going to take a look at the rotational equivalents. So give me a second to do that. These are the terms that we spent 6 units talking about, and we're going to look at the rotational versions of these terms. Physics people aren't very creative in their terminology, and so instead of talking about position linearly, we talk about angular position. You know, not very rocket sciencey. The symbol theta, the unit is the radian, or the rad is what we shorten it to. They're not going to be doing calculations in their calculator in terms of radians, like the cosine of pi over 2 radians, but that's just the unit. And if they understand the unit circle, they don't like the unit circle, there we go, we're right back at the unit circle. Angular displacement, delta theta, radians again. Angular velocity, see, we're not particularly clever in our terminology. Velocity is meters per second. We're not talking meters, we're talking radians. So it's radians per second. The unit, that is not a W, that's a lowercase Greek omega. Angular acceleration. You see, These terms aren't particularly rocket science. The units might be a little bit different. The symbols are definitely different, but they're on the reference sheet. There's two big terms in rotational motion that are challenging to understand and to get through. One of them is our rotational equivalent to mass, which is referred to by different ways. I'm going to call it rotational inertia. And we're going to talk about that more in Unit 7A. This has the symbol I, capital I. The units are really weird, not that they need to know the units, but kilograms, meters squared. The other unit they've heard of, they don't necessarily know what it is the rotational equivalent to force, which is torque. The symbol is the Greek letter tau, and the unit is Newton meters. Not to be confused with work. Work is force times distance. We also have the unit Newton meter, but this, which becomes a joule, but this is not that. This is the Newton meter. I've never seen where kids have gotten confused with that. And then finally, momentum. We have, shockingly enough, angular momentum. The letter represented, or the symbol for it, is a capital L. I don't really know why. I'm sure I might have known why at some point in time, but I don't anymore. And it is Newton meter seconds. Kind of weird, but quite honestly, they should practice calculations with rotational kinematics, which I'll introduce in 7A. Most of this is very much of a qualitative unit. The other thing to keep in mind, with linear terms, we had vectors. Well, we still have vectors. Here, the vectors, if it was a negative vector, it went to the left. If it was a positive vector, it went to the right. You can't see that. I apologize for that going off the board. I go left. That's a little better. And I go right. So I'll put it up here. We also have vectors rotationally, except now we have to capture it in terms of which direction is it going. If it's going, I always have to think about it. I know if it's going counterclockwise, that's a positive direction. If it's going clockwise, that's a negative direction. So the way that I think about it is, I think about how my angles, how the unit circle's laid out. This is 0, pi over 2. If it's going that way, that's positive. If it's going that way, that's negative. That's how I have to think about it, because I have trouble with clockwise and counterclockwise. It's dumb, but that's what I am. Okay, so now let's talk about the big ideas. Like all my other units, I broke it up into parts A, B, and C. A talked about forces, B talked about energy, part C talked about momentum. I'm doing that again here. So my 7A is talking about torque. And keeping in mind, and the basic idea is, if the net torque is 0, the object's rotation is not going to change. No change in rotation. And if the net torque is not 0, we're going to have an angular acceleration. That results in an angular acceleration. So our rotational motion changes. Analogous. Same idea as with force. In terms of energy, I don't talk a whole lot about energy. I spend most of the time talking about rotational kinetic energy and how that affects the overall motion of the object. And even then, it's a very high level discussion. What I think what they do need to understand is, if the body is rotating, it has kinetic energy. Actually, what I call that rotational kinetic energy, and it's not what I call it, it's what it is. It's rotational kinetic energy. If it's moving and rotationally, that takes energy. The other item, which is a little bit bigger that you got to be careful about, is that total mechanical energy is still conserved, assuming we have a closed system. And so that's one thing that we need to consider, and I'll talk more about that in Unit 7B. Under my momentum unit, where I'm talking about angular momentum is to me, it's such a fascinating topic, but yet we really don't get into it very deep, simply because it does get very complicated very quickly. Angular momentum is treated as a very high-level discussion, but there are some very important aspects to keep in mind. If the object is rotating, it has angular momentum. If to change angular momentum, we need a torque. None of these ideas are truly different than the linear aspects of it. Nothing. None. I haven't hit upon anything else. I will say angular momentum and how we determine that does get a little different than linear momentum, but I'll talk about that in 7C. Angular momentum is conserved. Again, closed system. And we'll talk about what the closed system means. Well, when we'll talk more about what closed system means with the angular momentum aspect in Unit 7, in Unit 7C. And then the last thing to mention, and this is a little differently, angular momentum, linear momentum are separate, meaning we cannot take linear momentum and transform it into angular momentum, and vice versa. And so when I talk about momentum in Unit 7C, I'll touch upon this topic. This is a very important idea. So these are the big ideas to rotational motion. Let's get started with Unit 7A.